Okay, I assume that that's started sharing by now. So as you mentioned, my name is Stefan Borozan, and today I will be presenting my recent paper in Advances of Applied Energy, titled Strategic Power Network Expansion Planning with EV Smart Charging Concepts as Investment Options. This work has been conducted in supervision by Professor Goran Sturbat and Dr. Spiros Gianellos, and it's part of the IDLES program at Imperial. Um, so to give a little bit of a introduction to the topic, um, so firstly, we say that we are undergoing an energy transition, which is primarily driven in response to the threat of climate change. Now, this transition is, of course, accompanied by many changes in the technological landscape and also system operation paradigm changes. And it is crucial for infrastructure to adapt in order to enable these paradigm shifts and to facilitate the energy transition. Uh, Now, let's take electric vehicles as an example. The electrification of transport seems inevitable at this point, but it will cause an increase in electrical demand. Now, due to the nature of electric vehicles and the driving habits of people, it is expected that this increase will be locationally non-uniform, and also that it will be concentrated within a few hours of the day, causing a disproportionately high demand peak. Now, the consequence of this is that large and expensive infrastructure reinforcements would be required in order to accommodate the charging of electric vehicles, even though power lines could be underutilized outside of these peak hours. Furthermore, as we are in the midst of the energy transition itself, there are many unknowns over the future development of power systems, which leads to significant uncertainties. And uncertainties around these long-term developments create challenges in decision making, and therefore increase the risk of premature commitment to flawed network expansion plans. And it is for this reason that there is a real need for investment options that offer flexibility and for planning frameworks that can exploit it. So in my presentation today, the focus will primarily be on the electrification of transport as the driver for investment. But I will also focus on turning the challenge of accommodating EVs into an opportunity by using the flexibility coming from the electric vehicles. To quantify the benefits of the mentioned approach, I will be using option value. And what that means is that, well, investment flexibility essentially enables a wait and see approach to decision making, where decisions to invest are made between an irreversible and capital intensive project and a flexible alternative, which then gives the option to later make these big investments or not. Essentially, that means that by using this flexible option, we can defer or completely displace large-scale investments. And real options theory, an approach based on real options theory, is necessary to quantify the value, the real value of this flexibility. And to do so, we need an adequate modeling. To demonstrate the concepts, I will talk about a case study on the power system of Great Britain. To demonstrate these two crucial enablers for strategic planning, which are having an adequate planning model. In my case, that is based on stochastic optimization, and the role of smart investment options, and as I mentioned, in my case, EV smart charging concepts. Now, firstly, if we talk about long-term uncertainties themselves, let's assume this emoji is me, and I have been tasked with planning or creating a study for the expansion of a power system. And this can be a 10-year development plan, 20 years, 40 years into the future. Whatever it is, I'm looking at current trends, and there are many different variables that I need to consider that I wouldn't be sure about in the future. This can be, for example, the renewable generation capacity in the system, um, what power lines we will have, the uptake of electric vehicles, the electrification of transport, that is, which would cause different demand levels. So there are all these different sources of uncertainty that I need to consider. And in addition to that, there are four different characteristics, four different aspects to each of them. So the first one is where, which would be the locational aspect. So in terms of electric vehicles, where will electric vehicles appear first and second and the third? The second is the timing. So when will electric vehicles appear? The third is how, or rather the technological aspect. So what sort of charging technology will we have? What rated charging power will they use, etc. And lastly, the fourth characteristic is how much, or the extent to the electric vehicle penetration when we're using that example. Now, in the real world, there are people actually doing this, who are tasked with presenting with in-depth research into current trends, future projected trends, to kind of develop different scenarios or system development plans for the future. And in the UK, sorry, in Great Britain, that is National Grid, who put together the future energy scenarios. And in their latest iterations, they're focusing on four different scenarios, or rather pathways. The first one, the most ambitious, being leading the way. The second is consumer transformation. The third is system transformation, and the last one is steady progression. As you notice, the first three are able to reach a net zero power system by 2050, so reach the government's targets, whereas the last one is more conservative and it doesn't do so. Now, if we look at these different pathways on an axis, so looking over the timeline, we can have something like this. And it almost, in this case, doesn't matter. I'm just trying to show the concept. So it doesn't exactly matter what this is showing, but for the information, it's the amount of industrial and commercial demand side response in the UK. But as I mentioned, it can be anything on the y-axis, and on the x-axis, we have the years into the future. We see the historical data that we have, and then it fans out into four separate realizations over the years. Now, an intuitive way or an easier way to understand how this uncertainty and how the different sources of uncertainty interact and how they will realize into the future is by representing them on a scenario tree. So this very simple scenario tree here shows the left picture by having the root node, which is the current situation, and then four distinct scenarios representing the different future energy scenarios by National Grid. And it's divided into four separate stages: the current stage, the year 2030, 2040, and 2050. Now, if we look at one source of uncertainty in more detail, we can even expand the scenario tree to present a more in-depth study into whatever it is we're researching. And in this case, for example, if we look at the penetration of electric vehicles, we can expand the scenario tree to include 16 distinct scenarios. It's a multi-stage representation showing the realization of the multidimensional uncertainty. So to recap briefly, we saw that long-term uncertainties are multidimensional, subject to different characteristics, and we can represent them using a scenario tree. Now, the issue in planning is that, well, all these different nodes that we see in the scenario tree are actually decision-making points. We can make investment decisions in all of these. But there are some nodes that are critical nodes or that are common for multiple scenarios. The most extreme example is the root node, the first one here, which is common for all 16 scenarios in the tree. And any investment that we make here will apply to all scenarios. The implication of that is that, as we see the bottom scenarios here, following the steady progression future energy scenario, they are more conservative. There's less of a demand increase, whereas the uppermost scenarios are more ambitious. They have a faster uptake of EVs and higher uptake of EVs in 2050, for example. Now, investments may be necessary for these, the top scenarios, but not the bottom ones. So any investments we do here may end up being stranded if one of the bottom scenarios occurs. So this introduces the notion of regret. Regret can come in the form of overinvestment, where we make too much investment preparing for a certain scenario, another one occurs, and then we have underutilization of assets and stranded costs. Or it can be underinvestments where we are underprepared, we don't make the correct investments, and if one of the topmost scenarios occur, the system operator will be forced to curtail some load, which is very costly as well. So thereby comes this need for planning frameworks that enable strategic decision making. So that's the crucial thing. That's the first thing we need for strategic planning, to take into account this uncertainty. And we've developed the stochastic network expansion planning framework, and the figure on the left shows a quick summary of it. As input, we have the different EV charging profiles. These are extracted from statistical data, from historical data using statistics, to develop different charging profiles depending on the different electric vehicle fleets that we're using, whether residential, commercial, industrial, and so on, and also for different days of the week. So we see some variation between work days and weekends because of different driving habits. And there is some variation between seasons as well. Secondly, there's demand and generation representative data. And so these two aspects we kind of cluster them, we package them into representative days or weeks, depending on the size of the case study and our computational limits. But we can basically represent the variability in system operation via representative blocks. Then we input the network topology and obviously the scenario tree parameters, which describes the realization of uncertainty. Then the model itself, as mentioned, it's a multi-stage stochastic optimization model, and it also involves the modeling of the investment portfolio, which can be line reinforcements, or I sometimes refer to this as conventional investments, and smart options. The model gives as output the long-term investment strategy, as I mentioned earlier, by giving us what investments we need to make in each of these nodes, and also the option value of the smart alternative that we're considering. To look at the stochastic optimization in more detail, it is a node variable multi-stage stochastic optimization problem, and the deterministic equivalent is a mixed integer linear program. So just for some notation, M represents a node in the scenario tree, and so this pi M is the state probability of node M. So in the objective function, we have the investment costs. Sorry, these are discounted to the present value. So we have the investment costs and system operation costs. Investment costs are comprised of the line reinforcement costs, which are subject to a fixed costs and a variable cost per megawatt. And also smart investment costs, which are subject to a unit cost per, in our case, a charger, one single charger. Then we have the system operation costs, which are comprised of, which we calculate for each scenario tree node and for each representative block. And they're comprised of generation costs, load reduction costs, as well as demand curtailment costs. Our objective objective function is subject to investment constraints, which contain some integer decision variables, making it a mixed integer linear programming, as well as system operation constraints. And this can be generation constraints, power flow, etc. Now, this is a very, very large scale problem. And to solve it, we need to employ some sort of decomposition or solution algorithm, and we've opted for a hierarchical multi-vendor decomposition. Now, the way it works, we decompose the problem into an investment master problem, which solves the investment decisions across the scenario tree. And as I mentioned, it's only investment decisions. So we get rid of the system operation aspects of problem and substitute them with an approximation of system operation costs using this variable alpha. It is still a mixed integer problem, but it's a lot smaller. And we append these Bender's cuts, which are used to help us approximate the system operation costs. Then the problem is decomposed in multiple system operation subproblems, and we have one for each scenario tree node and representative block. But in this case, we fix the investment decisions, and so we can get rid of the mixed the integer part of the problem and the and the investment part of the objective function, and we only solve system operation, subject to the regular constraints. When doing so, we also obtain the duos of the complicating variables, which are the investment decision variables, to then be able to construct the Bender's cuts. This is an iterative approach. So if we start in the first iteration, we solve the master problem. We obtain investment decisions and the corresponding investment costs, and an approximation of the system operation costs. Then we have multiple subproblems which we can parallelize, solve them in parallel, and obtain the expected operation costs as well as the duals that I mentioned. We can check the convergence criterion. If it hasn't been reached, we construct a Bender's cut for each of the subproblems that we have and append it to the master. This process continues until we can reach a convergence and we obtain the network expansion strategy and the associated costs. Now, let's look at the long-term expansion of the GB network. So, firstly, we have a reduced Great Britain transmission network, which has the current information on generation, storage, and energy storage, and interconnection capacities. So it's quite up to date. It also has realistic assumptions on the long-term uncertainty, because we use the future energy scenarios as the underlying scenarios for uncertainty, as I described earlier at the start of my presentation. And if we look at the plots on the right, these are from the future energy scenarios. We see showing, so there are 4 of them. The top plot showing the generation capacity in the years 2020, 2030, 2040, and 2050. And the bottom plot shows the level of demand in gigawatts for the same scenarios in the same years. Without going into much detail, we see that they differ quite significantly. But also, as mentioned earlier, we've expanded this uncertainty to look at EV uptake in specific. So it's the four scenarios are expanded into 16 scenarios, um, which include further uncertainty into the level of the extent and timing of electric vehicle optics, the smart charger costs, and also drivers' participation in smart charging. And what that means is that a driver could have access to a smart charger, but may choose not to participate in any smart charging because, for example, they have an important trip in the morning and they want to make sure their electric vehicle is fully charged at 6 a.m. So as I mentioned, there are 16 scenarios over 40 years and separated in four stages: the present stage, the year 2030, 2040, and 2050. We also include 8 representative days to capture the seasonal effect. So we capture 4 different seasons and also weekday and weekend variations. We look at the residential electric vehicle fleet of Great Britain, and we assume that electric vehicles charge with 7.4 kilowatts, and their batteries are 50 kilowatt hours. And this is in line with the future energy scenarios modeling of National Grid. Firstly, let's look at the expansion plan when we only have network capacity investment. So essentially the conventional approach. The expected system cost in this case is £94.7 billion over the 40-year horizon. And secondly, we see that there are investments in the first stage, in the second stage, and some in the third stage. This essentially tells us two things. One, that the multi-stage stochastic formulation does provide some level of strategic decision-making abilities, because we see that not all investments are made in the early stages, but we have some in stage 3. However, it also shows that a lot of investment is necessary upfront. So some of these lines or some of the capacity investment here may not may actually end up being stranded in certain scenarios. The maps on the right show us the cumulative, so the total, so all investment, network investment projects necessary up to the year 2050 for the different scenarios. We see that the investments are mostly concentrated in Scotland, in one area of Scotland, and then certain lines across England that need to be reinforced. Now, this approach still leads to some overinvestment. And by looking at the plot here on the left, we see, so the red stripes here show the amount of overinvestment. And we see that it happens in all scenarios except for scenario 1 and scenario 5. That's not ideal. So just to mention, in this case, overinvestment was determined with respect to the optimal deterministic expansion decisions of each scenario. So in that case, the issue of common nodes does not apply. And because the deterministic approach assumes perfect foresight of the future. And so we get the exact amount of capacity that we would require in future in each scenario. And now the risk of overinvestment in this case, it amounts to just over £132.9 million, and it has been calculated as the sum of probability-weighted stranded costs for each scenario. So as we see, it's quite significant. So the second thing we need to mitigate this and could potentially be planning with smart investment options. And this is because conventional network infrastructure investments are bulky, so they're very large scale, they're expensive, they're irreversible, they have very long commissioning times, and they offer very limited flexibility, as we saw, and only with an appropriate planning framework. On the plus side, they do offer some economies of scale. But when we look at smart solutions, or rather non-network investment solutions, as has been proven in literature for energy storage, demand response, and similar technologies and concepts. Um, they are, so firstly, the positive, they are smaller scale and they have much quicker project completion. They offer flexibility in terms of investment and also system operation later on. The downside is that they're currently considered as expensive and subject to regulatory and market barriers. But I've put question marks there because the technological landscape is changing, so technologies are becoming cheaper, and also the barriers are being slowly removed. And they're also country specific, so today's audience comes from all over the world, and it might not be the same case everywhere. So essentially, if we integrate these smart solutions into the investment portfolio, we could enhance the investment flexibility, which would allow us to defer and displace conventional investments. With this, we can consider smart solutions or smart investment options as hedging tools against uncertainty, which would help us reduce this risk of overinvestment. Now, looking at electric vehicle smart charging concepts, we have modeled grid to vehicle, firstly, which considers unidirectional charging. So the charging process of the electric vehicle can be paused and delayed to a future time. So essentially doing load shifting. We've considered vehicle to grid, which has bidirectional charging, which means that in addition to pausing charging, we can discharge some of the stored energy into the grid, directly into the grid. The state of charge of the vehicle-to-grid fleet is modeled as aggregated mobile energy storage units. And what I mean by mobile is if you look at the equations on the right, description of equations on the right, the sigma here represents the state of charge. And we see that we updated based on the previous state of charge, so the state of charge in the previous time period, the current V2G operation, in terms of charging and discharging, and also the state of charge of any arriving and departing electric vehicles. And that's different from standard energy storage modeling. Finally, we have vehicle to building, which similar to V2G has bidirectional charging capability, but the discharging happens locally, only to supply load to the building in which the vehicles are connected. And the implication of that is the discharging, so the operation limits are constrained by the aggregated power limit of the electric vehicles or the building load itself, whichever is lower. In terms of the load range capabilities, what does this mean? Well, let's assume we have N aggregated electric vehicles with a rated power of PR. The uncoordinated charging, it just means that vehicles would require the same amount of kilowatts. With the G2V, this translates to a range between 0 and the uncoordinated or the total aggregated load. With V2G, though, we see that this can additionally become negative due to the discharging abilities. So essentially, we can have a negative load from the grid's perspective. And finally, vehicle to building, as I mentioned, we can have two different scenarios where the constraint is the constraint on discharging is, or rather the load reduction capability is constrained by the number of aggregated vehicles, or if the demand of the building is lower, then we would be constrained by the demand of the building. So there are three questions that I'll try to look at and answer in the case study following. The first one is, are G2V, V2G, and V2B viable non-network investment options? The second question is, can smart charging investments be used to hedge against uncertainty? And three, what is the value of planning with smart charging concepts? Now, firstly, to look at the case where we have the ability to invest in the network and also in G2V enabled chargers. The scenario tree on the left shows the previous example that we had with conventional investment only, and the one on the right is conventional and the G2V. The first thing we notice is that the expected system costs have reduced. That's a positive. The second thing that we notice, if we look at the blue circles, is that some lines that have been invested, that we've decided to invest in the conventional approach, are no longer there in the approach with G2V, or they have been pushed back to a later stage. For example, if we look at this node here, that's node 4, we see that this line 410 still exists. However, line 1213 has been moved here to the third stage, so it has been deferred, whereas line 910, so line connecting the buses 9 and 10 in our GB network, is completely displaced. So we don't need to commit to this infrastructure reinforcement project. And this translates to some differences in what the total investments up to 2050 look like. For example, noticeably, we can look at scenarios 15 and 16, where we have this line here missing. We don't need to commit to investing in it anymore. If we look at the case of network and vehicle-to-grid investments, the first thing is that the total expected costs have reduced even further. Secondly, and very importantly, we see that the first stage decisions, I'm sorry, I forgot to mention this. In the grid-to-vehicle case, the red circle here shows us that the first stage decisions have not been moved. So despite the flexibility offered by G2V, we can't defer or displace the first stage decisions. Whereas in the case of vehicle to grid, we see that these 3 lines are no longer present in the first stage, which means that in the present state of the system, we don't need to commit immediately to these large scale and expensive infrastructure projects. And with that, we avoid a lot of regret in future. Looking at the maps again, so looking at the investments up to the year 2050, we see a lot of difference across all of the different scenarios. And so I haven't put any marks, any circles here, because we can see differences everywhere. Finally, looking at conventional reinforcements and vehicle to building, we again see a reduction in the total expected costs. And we also see that vehicle to building is also able to displace or defer these first stage investment decisions. The maps of investment projects look very similar to vehicle to grid as well. Now, to summarize and to quantify these benefits, we firstly see that when planning the expansion of the GB power system with smart charging concepts, it generates substantial economic savings with respect to the conventional only approach. In terms of option value, for grid to vehicle, that is £1.2 billion. For vehicle to grid, that's £10.7 billion, and for vehicle to building is £10.1 billion. And again, this is across the 40-year planning horizon. Now, we've also noticed that option value is largely driven by system operation costs. So the flexibility of the system operation flexibility enabled by these concepts is actually what drives this large value of this large option value. And that is the reason why we see such a large difference between the unidirectional G2V and bidirectional charging of V2G and V2B. However, despite the lower value of G2V, we can see that it's very, very effective in mitigating overinvestment and mitigating this risk of overinvestment, which it used to be 133 million or over 133 million pounds, and now it has been reduced to 18 million pounds. And we see that for the case of grid to vehicle, so if this plot here is showing the amount of network capacity invested for case, and the red stripes again show overinvestment, and we see that grid to vehicle, the case of grid to vehicle has overinvestment only in 2 of the 16 scenarios. On the other hand, planning with V2G and V2B completely eliminates this overinvestment risks. To summarize the benefits of planning with smart charging concepts, firstly, we saw that there is investment flexibility by, again, deferring and displacing conventional investments. And also, we have enhanced network asset utilization. So firstly, that's through lower capacity investments. And also the congestion mitigation ability of optimized. We're able to mitigate congestion, network congestion, through optimized EV charging operation, which means better utilization of network assets. And to demonstrate the importance of this, I will use this is the leading the way future energy scenario, which in our case is scenarios 1 to 4. And this plot on the left shows the number of electric vehicles present. We see that there's a very sharp increase up to the year 2040, but then it actually reduces. The scenario envisages lower electric vehicles in the year 2050. Now, this essentially translates to slightly lower electrical demand. And when we have the conventional only case, we see around 5.5 gigawatts of investments, of network capacity investments, which once we get past the year 2040 would end up stranded because we don't necessarily need all of this capacity. Whereas all the other charging concepts are able to reduce the amount of network capacity that is invested, and thus eliminating, or in the case of G2V, mitigating this overinvestment. Finally, we have wider system benefits that are essentially unlocked by the presence of smart charging in the network. As I mentioned, there's enhanced system flexibility in system operation, which translates to renewable generation curtailment mitigation and CO2 emission reduction. On the plot on the left, we can see the 4 different cases that we looked at and how what that means for renewable curtailment. And on the plot on the right, we can see the CO2 reductions compared to a conventional only case. And I just want to point out that even that G2V, despite its lower option value, it's still able to achieve almost 15% of CO2 reductions. Finally, to conclude, so we can answer that EV smart charging is a viable and highly valuable investment option when facing long-term uncertainties. We saw that vehicle to grid and vehicle to building have significantly higher option values compared to grid to vehicle. And a noteworthy observation there is that V2G holds obviously the highest economic potential, but vehicle to building has a comparable option value to it at transmission level. However, it additionally provides further benefits in terms of energy management of the building to which the EVs are connected. So if we look at a distribution network scale, we might see somewhat different results. And also, it means that the choice in future between the 2 concepts could be made based on other socioeconomic or technological aspects. For example, the availability of connections, grid connections, that is, charger connections. Then we also saw that there is significant deferral and displacement of conventional projects, translated to investment flexibility and risk reduction. We saw that significant system operation savings are achieved when planning with smart charging concepts, and we have improved network asset utilization and wider system benefits. Now, if we look at this figure on the right, what essentially tells us it's a comparison between the business as usual case and our proposed approach, where the challenge is common for both, where we have an uptake of electric vehicles and an uncertain demand growth in future. Now, the conventional approach applies only network reinforcements in usually, in most cases, the deterministic fashion, which would lead to an expensive system operation and expansion, so investment strategy, and also doesn't do much for the integration and the accommodation of renewable generation. In our research, we proposed the three linear models for G2V, V2G, and V2B investment and operation for the integration in large-scale network expansion problems under long-term uncertainty. So the multi-stage stochastic framework successfully identifies the strategic actions by deciding sort of the optimal locations, sizes, and timing of smart charger investments in a way that conventional reinforcements are deferred or displaced, which, as we saw, leads to economic and environmental benefits. And that is what this green side of the figure represents. So essentially, this research will talk about making strategic smart charger investments to facilitate EV uptake and decrease system costs under uncertainty, essentially preparing the grid for the mass uptake of electric vehicles while simultaneously leveraging opportunities from electric vehicles as solutions rather than seeing them as a problem in our energy transition. For further details on this research, I would welcome everyone to look at the paper that was published in Advances in Applied Energy for a more detailed view on the modeling and the theory. But there's also a blog post by the Energy Futures Lab of Imperial College, which looks at a more high-level summary of the benefits. And I would invite everyone to look at the IDLES program at Imperial College, which brings together researchers from different departments to provide a sort of a comprehensive evidence and comprehensive insights into how to facilitate a cost-effective and secure transition to a low-carbon future. Lastly, just very briefly to look at the future research that I'm currently that we are currently doing. So the main bottleneck in any large-scale stochastic optimization problem is the computational performance. So there is a limit to how much modeling detail can be implemented before the problem becomes intractable. So our number one goal, so the first goal is to implement a is to improve the computational performance and shift the tractability limits of our model. We're aiming to do so by implementing a superior solution algorithm based on a nested Benders decomposition and integrating machine learning methods into the optimization framework itself. Once that is done, we aim to introduce further modeling complexities. For example, modeling short-term uncertainties, applying the model, or rather making changes to the model to be able to apply to distribution network planning with decision-dependent uncertainties, in addition to the exogenous uncertainties that we looked at today, and also expanding the investment portfolio with multiple smart options, which we can currently do from a modeling perspective. However, we can't include too many options as the problem, especially to very large-scale case studies. So yeah, thank you. That is my presentation today. Feel free to email me with any questions or feedback. And also, as I understand, we will take some questions now. So would you like me to stop sharing the screen, or I imagine some people would like to go back to certain slides. Aha, we cannot unmute ourselves. How can we talk?
Stefan, you may check the chat box.
Yeah, so I just saw the message that ye can't unmute, so I will look at the questions myself.
We should ask the host to how to unmute.
Yeah, that's okay.
Including the chair.
That's tricky. But okay, in the meantime, I can see that there's one question so far. Thank you, Stefan, for the wonderful presentation, very informative. My question, how do you go about assuming or forecasting the EV fleet, number of vehicles, and number of chargers in 2050? What's the ratio of chargers to cars? Okay, so there are multiple ways of assuming or forecasting the future that have been proposed in literature and that are being undertaken, usually involving some sort of clustering techniques after in-depth analysis of current trend, historical trends, and expectations for the future. This research in particular did not look into these methods. We instead used the assumptions made by National Grid as the base assumptions. And they have made these assumptions on the EV fleet in future. The reason why I decided to look at to take the National Grid future energy scenarios is because there's a lot of resources that go into preparation of this future pathway. So they look at all sorts of socioeconomic, political aspects, they look at technological aspects, etc., etc. And so these are very informed assumptions for the future. So yeah, I mean, I don't know if that answers your question in terms of how do you go about assuming the EV fleet, but essentially in this case study that I presented today, it was a very in-depth analysis which can be found in the National Grid future energy scenarios. And in terms of the ratio of chargers to cars, so what the underlying assumption in our model is that charging, so uncoordinated chargers, will be made available exogenously. So they will be made outside of our model for any electric vehicle that needs it. So there will be enough charging infrastructure for cars to charge following the dumb charging approach, as we call it. And what our model does is it identifies the number of chargers and the location of smart chargers that need to be invested. So when we looked at the scenario trees earlier with the investment decisions, those numbers there for the chargers they are only smart charger investments, not conventional chargers. I hope that answers. I hope that was clear.
Okay, finally we can speak now, and we can unmute ourselves. And I would like to take this opportunity as I'm not a host, but how to say? I just want. I have two questions. The first one is that maybe your case studies are based on some settings. For example, the penetration level of renewable energy, and also the different scenarios for carbon reduction, or just like the question asked by vendor. So it's you have the boundary condition about the electric vehicle and number of chargers or something like that. So how your result will be influenced by this kind of conditions or settings?
Quite. So the idea is that, or the limitation of any planning approach that considers uncertainty is that the results are highly dependent on the underlying assumptions on uncertainty. So the projections, the assumptions that we make for the future. And in this case, that as I was saying earlier, that's mainly the reason why I chose not to do it myself, but to take information from somewhere that a lot of research and resources have gone into.
Okay.
We have done some sensitivities in terms of how the uncertainty affects results. And we can see some differences, but not, we see differences in the expected costs. But in terms of investment decisions, it's quite similar, unless, again, the assumptions on the future level of renewable capacity or demand are entirely different. So with small changes in uncertainty, we don't difference in the investment decisions.
Okay. The other question is about the how to say, you say electric vehicle smart charging as an investment option. Yes. So if we investment something, we will get benefit or get money from the investment. So how to say, we save money from for smart charging. So how to incentivize this kind of electric vehicle for smart charging?
Mm-hmm. So our approach, we're looking at it as sort of a central planner approach, and a whole system level. So essentially identifying the locations, timing, and number of smart chargers that we would require. However, in industry, the people looking at this will not be the same people as making those investments. In most cases, I'm generalizing here, but in most cases that is true. And so the aim or the use for this model and this framework would be to identify where, when, and how much smart charging we need, and then develop adequate adequate incentives, either through policy, financial rewards, or in some cases it might be direct investment, depending again on who's planning and who has the ability to invest in charging infrastructure. But essentially, let's say in a liberalized market, this would be done through adequate policy.
Yeah, exactly. Yes, makes sense. Because I believe in your model, the electric vehicle are controlled centrally, yes, instead of incentivized by price single or something like that. So maybe we need to, how to say, provide a way to share this kind of money to this kind of to smart to these electric vehicles or charging infrastructures. Yeah.
Absolutely, yes. So essentially, such a planning framework can be used to inform decision makers, policymakers on what needs to be done and how and what is the value of these smart charging concepts, to then be able to develop adequate policy. Whereas in terms of operation, obviously we would need to look at different models for the charging operation.
Okay, great. So